Hi everybody, my name is Karl Smink. I am a PhD student at Mississippi State University, and I'm going to talk to you about some of the research that I'm doing on typing in virtual reality. So I'll give you a little bit of developmental history and motivation for the study, and I'm going to talk about the current ways that we type in VR. So you can type on a 2D QWERTY keyboard with your fingers. You can type on a 2D QWERTY keyboard with a laser pointer. Or you can type on a 2D QWERTY keyboard with drumsticks. So what do all of these methodologies have in common? They suck. So that's not just opinion. I have some data here. So these green bars, these are words per minute, average words per minute for how quickly you can type. These orange bars are percent accuracy. So we have our golden standard here, which is a desktop computer with a standard 2D QWERTY keyboard using touch typing. This is averaging about 60 words a minute with 97% accuracy. This is good. Mobile phones, just your phone with your standard 2D QWERTY keyboard on your phone, we go down to about 36 words a minute, so a little more than half. Our accuracy is still really good at 97 or 98.7% on average. So when Apple was developing Swipe, one of the first text-based input methods for mobile phones. When you put your finger down, you move it in a pattern, and then you let go, and it submits a word. When Apple was doing their user testing for that methodology, they said the users won't have anything to do with it, they don't like it, they won't touch it, until the accuracy gets to 95% or higher. That was the bare minimum threshold. So with that in mind, let's look at these other three VR methods I just talked about. So our words per minute with using the drumsticks drops to 25. So we're now less than half of our productivity on a standard computer. Our accuracy drops to 93.8%, which is below the acceptable threshold. But it's kind of close. If we use a QWERTY laser pointer, we drop down to 15 words a minute, and our accuracy drops to 84%. This is not good. But if we use unintuitively, if you type on a 2D QWERTY keyboard with your fingers, like you would on your phone or a tablet, but you do it in VR, we drop down to less than 10 words a minute, and the accuracy is 76%. This is unusably bad. So, why? Why are these so bad? Why is the error rate so high, and why is the words per minute so low? So nobody freaks out. This triangle symbol right here is the Greek letter delta. And this is used in mathematics to denote a distance or a change between two different things. So how we're going to use it here is I'm going to talk about the delta between your home row, sort of where your resting position is for a given typing method, and where any given key on this map is. So if you look here on a standard QWERTY keyboard using touch typing, your home row keys here, and technically the space bar, these are all of delta 0. That's where your fingers rest. You don't need to move your hand to click those keys. All the keys on the top row here would be delta 1, because you need to move any finger one key away to click that. Ones on the top row would be delta 2, etc. So the average delta to click any key on a not full, this kind of QWERTY keyboard, is about 1.2 keys. Everything is very close to your home row. Now, this is a little different. So this is the VR finger typing one. So these two purple keys right here are your two home rows, as close as you can get to the center of the keyboard. So these are going to be your delta 0s. These blue are delta 1, green is delta 2, light green is delta 3, yellow is delta 4, delta 5, and delta 6. So your average delta has more than doubled to 2.8. This is not good. This is if you're using a laser pointer, you only have one home row key, so to speak. You have 1 point of entry instead of 8 to 10. And your average delta can go up to 9. So your average is at 3.8, over triple touch typing on a standard keyboard. So the significance and sort of impact of all this is that your words per minute affects your productivity and usefulness for whatever tool or interface you happen to be using. And your accuracy not only affects your productivity, it also affects user frustration. How likely are they going to be to use this thing? If it's terrible, they won't use it. So both of these are big problems. So this is a single screenshot of the interface that I'm developing. Here is sort of your home row key where you hold your hand, and you can either grab that key or you can use a point cursor that follows your hand to select that key. But you can see there's only 8 letters here, and that's not enough. We need more than 8 letters. So I'm going to hop back and forth between these 2 slides to explain here. So in this method, the orientation of your hand affects which layout you get. And so as your hand changes from rotation from palm up to palm down, we get a different set of 8 keys for each one of these. So what this does in principle is it lets us lower our delta between any given key. If this is your home row, to get to this key is delta 1. If we need to go to a different layout, that's 1 delta, and then another delta to hit that key. So the highest delta we have on this keyboard is if your hand is at the exact wrong orientation, and you have to go 1, 2, 3, and 4 to click a key. Your highest delta is now 4, so we drop the average all the way down to 2.5, which is lower than all of the other VR text entry methods. So here is a very grainy old example. So you can type with both hands, or you can type with one hand if you have accessibility reasons or you need to do something with another tool. But you can grab a key. It'll still follow your rotation. You move your hand or your point cursor to intersect keys in order to insert them. And when you release your grip, it submits the word. So we're going to talk very briefly about how we do this quickly, because the English language, depending on which source you use, has over 500,000 valid words in it. So you can't, if you want to do error correction or spell check or autocomplete, that takes a long time if you want to loop through more than 500,000 rows every time I submit a letter. So we take that same dictionary and we put it in a structured tree. So here you can see this is encoded the words. Each letter for the alphabet has its own node, and then its children are the valid letters that come after that in the alphabet. So here we encode A, N, D, and this gives us and as a terminating leaf. We have A, N, T, and that gives us ant, and so on. So we can encode a tree like this for all English words. So we have P-O-T, pot, P-A-S-T, past, P-A-S-S, pass, and P-A-R-T, part. We can encode all the English words this way, and it is less space efficient to do that than to store them verbosely or to use a hash map. But the benefits are time complexity, which is our key thing. If I need to be typing at 30 to 60 words a minute, which is in order to compete with mobile and desktop, that's the target, I need to be able to find and execute these auto-completions or spell checks in near linear or linear time. And that's what this allows me to do. So it lets us avoid collisions like hash maps. It has really efficient prefix matching. So if you mistyped the first letter, it can take the rest of what you've typed and check other valid words that start with a different letter and offer you those as options when you go to submit that word. So it increases the accuracy rate, so you don't have to backspace through 10, 20-digit word. You can just submit the correct one. So this is me. This is my link tree. This has all of my contact information in it. You can import it directly into your phone. It also has links to my YouTube channel where I post updates on some of this stuff. This is my glorified doing business as company. You can work with me, or you can partner with Mississippi State University if you'd like to work with me on this interface, as I'm developing it for my dissertation next semester. And are there any questions?
Yes, quick question, maybe I missed it. It's,
Fabien, go ahead.
Yes, thank you. I'll do that. So I see the cost, which is the delta, or the way to optimize for, basically. What I maybe have missed is what I see as a way to, as a cost. Let's say if I tried this afternoon, then it's like I need to remember those 3 poses, basically.
Yep.
So to me, that's a cost.
It is. So a reason you see 2D QWERTY keyboards used in a lot of VR implementations now is because people already know the layout.
Yep.
You don't have to spend time searching for those keys, and you don't have to learn the keyboard layout because you already know it.
Yep.
However, if you remember when you first learned to type on a QWERTY keyboard, maybe in primary school or in high school, you maybe had a week-long training session, maybe even a whole semester, where what you did was learn how to type on a QWERTY keyboard. There will be a similar upfront learning cost to learn the layout. But to reach a similar speed of text input, you have to do that upfront.
But are you measuring that? Are you measuring
Yes, that will be part of our study, is how many hours of training are needed to reach a certain baseline of user proficiency and what their WPM and accuracy is based on how much training they've had.
Thank you.
Back.
Please. Oh, yeah, yeah.
So I was really interested in your tree. It's a binary search tree, right?
It's not a proper binary search tree. It's a TRIE. It's a very specific to
right,
lexicons. Yeah.
So when you run into a situation kind of like sorry, words missing. Basically, when it refers like, hey, is this the word you're trying to spell?
Mm-hmm.
Is this the word you're trying to spell based on the grouping of letters that you've already inputted into the query?
Mm-hmm.
Would something more like a 2, 3, 4 tree be able to do something the same, since data storage is not really an issue these days?
Yeah.
So would that, do you think that would actually help with the implementation of basically auto-suggestion and what you're trying to do?
It's a possibility. There's half a dozen ways to skin that same cat. This happens to be one that's just very, very good on the time complexity margin. And especially when you start typing in VR, if you're using an autocomplete, proper nouns or words that don't exist that you need to add to the dictionary can be very costly and time expensive in order to insert them. Using a TRIE structure, the insertion for a new word is linear time. It literally just puts it right at the leaf node where it needs to go.
To expand on Fabien's question about, I'm curious, so Doug Engelbart, one of the things that has sort of fallen out of favor in terms of one of the things that he talked about was this H lam T stroke S, this idea of humans with a significant amount of training and skills to be able to receive, to gain proficiency. He wanted 2 weeks for people to learn how to use a mouse, that kind of thing. So this is one place in terms of the level of training that will definitely be required in order to be able to do lexing. Do you have a sense, based on that, what you could do with more training, or what a more invasive or wild way of doing things that would be more efficient with more upfront cost?
Yeah, part of what I am working on is sort of distilling and extracting some curriculum from how to learn to type on a 2D QWERTY keyboard, where you have limited keys, and these are the valid words you can type with those keys. A lot of that stuff is old enough to be in the public domain now, so I can take that curriculum and distill, based on my layout, these are the words you can type with just the red layout, just the green layout, etc., and pull that stuff in. And we will, I and maybe a few people in my lab will try to become expert level users so that we can use that as a comparison between the larger volume of participants we have to sort of test how much like where the curve is on time training investiture versus what the upper level of proficiency can actually look like.
Yes, so first, I like this a lot, I think it's really cool.
Louder,
Oh,
please.
sorry.
For the cheap seats.
Yeah. I was wondering, so are people actually willing to take the time to learn this alternate method of typing? And second, how would you market this to people?
I mean, marketing it as a product is not really my concern as a researcher. My concern might just be file the patent and let the companies come to me and let them decide. Alternatively, as far as like, how do I convince a user that they have to learn to do something? Also, not really my problem. But we've seen in software development and in game development that even with complexity and a skill differential, the users that want to do the thing will put that onus upon themselves, and you can't really force a user that doesn't want to do the thing to do the thing. So as VR gets bigger and becomes more widely spread, the typing issue is going to hit a point where it's not feasible to use anything else.
On that point, I'm so grateful for this kind of research that we're seeing here, because the reason we have Curity is because it too quickly became standard, right? We all know the issues with that. And what you're doing looks fantastic, and we have no idea if it's the best. That's the whole point of research. So to start now, while this is in its infancy, and how you market it, you just have to find the right kind of enthusiasts, I think. Because I do want to say in support of writing rather than speaking, when you speak, it's great. Speech to text now is flawless in many environments. But you're using a different, in many environments, not always, but also speaking doesn't involve editing, right? And editing is the hard bit. So if you speak, and then you have the cursor, and then you have to edit stuff. I mean, Blade Runner wasn't really good in this. That you've all seen Blade Runner, I'm sure, right? So I'm so grateful for, like Ken was talking about, what you're talking about now. Let's go in different and not based on other assumptions. Thank you very much, Karl.